begin with a scripture here. So this is Romans. Well, my phone has decided to do weird stuff. Oh, there we go. Romans chapter 12, verse 2 says the following. It says, "And do not be conformed to this world, but be transformed by the renewing of your mind, so that you may prove what the will of God is, that which is good and acceptable and perfect." So it's Romans chapter 12, verse 2. I'll begin with a word of prayer. Heavenly Father, we thank you again for this time we have to study your creation. Help us to understand more about calculus today. I just pray you'd encourage students, if they're struggling, just to do their best, Lord, each day for your glory. In your name I pray, Lord Jesus. Amen. So, was there a question about homework? Seemed like there might be. If not, that's fine. So, I still haven't found a replacement. It's just all over the place. I gotta find a better bottle. So today, I think I'm gonna move on here. I think we've seen a good number of examples of the logarithmic differentiation technique. So I'm gonna go on to the next topic, which is related rates, which is kind of what it sounds like, which is if you've got rates, maybe you can relate them. What is a rate, though? A rate is a time rate of change, typically, right? And so the thing is, now that we have calculus, we know that a rate of change is the derivative with respect to time, all right? The instantaneous rate. And so if you have a word problem where you've got some physical variables that are related by some equation, then we can differentiate that equation, and that will allow us to so-called relate the rates. And so that if you have partial information about it, you can kind of extrapolate from there. But there's a question, so go ahead.
This is a question. Sorry for asking this.
That's fine.
Can you do
191 or something similar to it. Let's see if I can find it. And by the way, I did mean to announce the homework problems for next week. I just didn't remember. Wait, is that from the Mission 4?
Yeah.
I don't have that one in front of me, actually. What was that problem?
It says assume f of n of a. Let me show it to you. This is a lot. It's one of the more questions.
Oh, yeah. So I will post a solution of this, like probably, well, hopefully soon, maybe later today. So maybe you should just wait and look at that. That's kind of a, probably better for me not to spend a bunch of class time on that. I did n equals 2 for that the other day. Like n equals 2 for it. Looks like this. If we take fg and we calculate prime prime of a, then I worked it out. It was f prime prime of a times g of a plus 2 f prime of a g prime of a plus f of a g prime prime of a. And so you could kind of guess where this is going to go. To get it off the bounce. What do you think n equals 3 is going to be? What's the third derivative look like? If we take the third derivative of the product. So if we understand the pattern, what's going to happen is we'll get the third derivative of a times g of a plus 3 times the second derivative of a times the first derivative of g plus 3 times the first derivative of f, the second derivative of g, and then plus the f of a times g prime 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 of a. Like you can work it out, that's what happens at n equals 3. If you look at this though, you can start to see what's going on is this. And so the relevant mathematics here is something like this. We can write the sum, if we have a plus b to the n power, it's the sum k equals 0 to n of n choose k, a to the power n minus k, b to the power k, which works out to like a to the n plus n a to the n minus 1 times b plus dot 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 plus n a b to the n minus 1 plus b to the n. So this is the binomial theorem. That's what I'm talking about there. And you can show that the nth product rule can be written in terms of the binomial. These are the so-called binomial coefficients. So those binomial coefficients we're seeing appearing here. So, and then I think to like complete the proof, you could do like a proof by induction. Suppose the formula holds for n, then you can prove the formula holds for n plus 1. But it is a challenge problem. I'm sorry, I said I wasn't going to talk about this. My bad. Other questions, preferably about the homework for next week. That one was already collected, so, you know. Nobody? All right, well, let's talk about related rates then. So, probably the easiest thing to do for related rates is to just illustrate by some examples. So I'll just kind of give you the general scheme here is some word problem suggests an algebraic relation, right? You're usually typically given some of the rates. You're given some of the rates, and then basically what you're going to do is you're going to differentiate the. I'm going to give the algebraic relation a name star. You're going to differentiate star with respect to time t. You need to use the chain rule. And then you can solve for the missing piece. All right, so let me give you a kind of silly, but not atypical example of this kind of analysis. So example 1, suppose the EPA adds oil to an oil slick such that the area of the oil, area of the circular oil slick, I can't spell slick, increases at 100 feet squared per minute. If the radius of the slick is equal to, let's say, 30 feet, then how fast is the radius increasing at this time? You know, somebody in the EPA, they need to create something so that they can solve it and get a promotion, you know? Something like that. All right, see here. The question then is, what's the equation, like, let me draw a picture. What's the equation here to think about for this exceedingly silly problem? So, you know, here's my oil, right? And it's circular, all right? So, and of course, I mean, okay, to be fussy, is it a circular slick? I mean, it's a disc. You know, circle's the boundary of the thing I'm talking about. But if this is the radius, let's say r, I'll use big R because my big R looks better than my little r. What's the area as it relates to the radius if it's a circular oil slick? A equals what? What's the area of a circle? Pi r squared, yay! All right. Hey guys, had me worried for a second there. No, I think you know that the area of a circle is pi r squared, right? We will eventually derive this in calculus, but we're not there yet. So we know that the area of a circle is pi r squared because we know, you know, basic geometry. And what else we know here, from this right here, see this? This I can interpret. That tells me what? That actually tells me that dA dt is equal to 100 feet squared per minute. All right? And so what I typically do in calculus is I omit the units except for the answer. So I'm going to want to do everything in terms of feet and minute. Watch out for this. If you've got a problem that's got a mixture of different systems of units, then you need to convert so all your calculations in the same system. But anyway, so we know dA dt is 100 feet squared per minute. So I'm trying to find, what's my goal here? To find what? Right, so our goal, exactly, how's the radius increasing, is to calculate what? That is dr dt, right? That's the rate. We're trying to calculate dr dt. That's what we're after. We know dA dt. We know that A is equal to pi r squared. How do we find dr dt? So, all right, so I think we have, everything's on the table here, all right? We see what we're doing, I hope. And so the next move, what you're going to do is you're going to differentiate the relation. So differentiate this gives me that dA dt. And what's the derivative of pi r squared? Well, it's 2 pi r, right? But I'm differentiating with respect to time. So since I'm differentiating with respect to time, let me write it down explicitly, ddt of pi r squared. Since we're differentiating with respect to time, we have to do the chain rule. So we've got 2 pi r times dr dt. See, now all we need to do is to solve for dr dt. All right, so this gives me dr dt equals to, did I ever move the camera? Can't remember. Looks like I did. So you guys solve that. So what do you got? We got dr dt equals to dA dt divided by 2 pi r, I guess. So what's that? That's 100 feet squared per minute divided by 2 times pi times r. What was my r? That 30 feet, right? And so, yeah, whatever that works out to. Let me, man, I hope I have my calculator with me. I really want to give you guys a decimal number for this one. But I think I might have left my calculator back in the, oh, nope, I got it, woohoo! So in calculus books, sometimes they'll leave answers like as fractions. So, especially something like this, you know, what's 100 over 60? That's just what, 5/3. So you might see this answer as like 5 over 3 pi feet per minute. That's, you know, a typical calculus book answer. But if I'm teaching physics, I would like, you know, the decimal form for the answer for sure. And that is 0.5305 approximately feet per minute. So this is related rates. Yeah? Let's look at another problem. Yeah?
So which form do you want here for the result? Do you want the physics form?
I'll take either.
Kind of
Yeah. In physics, in physics this semester, I'm trying to be a stickler for I want numbers for the answer.
yeah.
And you're like, well, they're both numbers. But okay, so my 10-year-old apparently was telling us, yesterday his mom told him that the answer to a problem was 34 over 7, and he's like, no, that can't be the answer. It's not done. That's a fake number. That's not a real number. So he's like, because you know, he's thinking of like, you can still divide 7 into 34, right? It's, you know, like 4 point blah, 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 you know. To him, the 4 point blah, 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 blah is the real number, you know. This 34 over 7, it's a division left undone. But anyway, but I will accept either. So. And for the record, rational numbers are real numbers. But anyway, example 2. A car goes on track with you know, equation, let's say 10x squared plus 6y squared equals to, I don't know, 20. All right, when dx dt is equal to 30 meters per second at the point, well, let's just say that when dx dt is equal to 30 meters per second, what you know, velocity is possible for y? So this is the equation of like an ellipse. All right, so you got the car's going around an elliptical track. And I'm telling you that its horizontal velocity is what did I say? 30 meters per second. And then the question is, if that's the case, then what's the vertical velocity? What's the dy dt in this situation? All right. So how would you figure it out? So this is, again, a related rates problem. So all you do is you differentiate the relation. All right, so we know that for this car, it's following this track like this, right? So the concept here is both x and y for the car, not care, good grief, are functions of time, t. So it makes sense to differentiate that equation with respect to time. All right? And so what we have is we have ddt of 10x squared plus ddt of 6y squared is equal to ddt of 20. We could solve the same problem, making the oval track like expanding as a function of time. If you wanted to, like you could replace this 20 with like a 20t or something, and then you can imagine like the track is getting bigger with time. You could still solve this problem if you wanted to. I'd need more information if that was the case, but I'm just thinking of a fixed track for the moment. And because of that, this is kind of boring. This derivative of 20 is just what? 0. Cool. And chain rule does the rest of it for me. So I've got what? 20x times dx dt plus 12y times dy dt is equal to 0. So what's the y? What is the y velocity for? What's the y velocity? So in this problem, I might ask, what's the y velocity? I might ask, what's the rate of change with which y is changing? Right? However you want to say it, what we're looking for, we're trying to find what? We're trying to find dy dt, right? Okay. So then what do? We solve this for dy dt, do algebra, all right? And what's that give us? We get dy dt is equal to minus 20x times dx dt divided by 12y, which apparently is, like, well, I won't try to simplify it. Minus 20x times what was dx dt? 30 meters per second divided by 12y. So with the given information, that's like all I could tell you. All right? So to make this problem more interesting, we should add more information to the problem, right? To make this problem more interesting, I could do what? I could add another piece of information to the problem statement. What velocity is possible for y? And let's add something. Given, I'm adding this now, x is equal to 1. Oh, see, if x is given to be equal to 1, then that forces y to be something, right? What is y going to be if x is equal to 1? What do we do here? So let's work it out. X equals to 1 tells me that 10 times 1 squared plus 6y squared equals to 20, which tells me that 6y squared is equal to 10, which tells me that y squared is 10 over 6, also known as 5/3. So therefore y is equal to like plus or minus the square root of 5 divided by 3. And now I can put that over there, all right? And I'm assuming that this is in units of meters and such. So, we've got like minus 20. X was 1. And I guess we could put a meter. I'll put meters there, 1 meter, just for the, let me not do that. The units for x and y cancel. Anyway, so we got 1, and we've got 30 meters per second divided by 12 times plus or minus the square root of 5 over 3. Let me work that out. I wouldn't want the answer left like that. I either want a simplified fraction or a decimal for these kind of problems, okay? Don't make me try to figure out what the number is for your answer. Please, clean it up. So 20, I mean, if your employer gave you a problem and you gave him back this answer, he'd be like, get out of here, I would hope. Let's see here, divided by square root, 5 divided by 3. It works out to 10 root 15, but I want a decimal here. So this is approximately, approximately 38.73 meters per second, and you could go plus or minus. Why are there two values? Let's picture what's going on. So this is some kind of, this is not like an exactly true picture, but the ellipse is something like this, all right? And so we've got that dx dt is 30 meters per second, right? And x is equal to 1. So like, you know, either you've got, you're like here, or you're like here, right? If you're here and you're going this way, you're doing what? You're going down, right? And if you're here and you're going that way, you're going up in the y sense, right? So if you're and you can see that here, right? If I choose the plus solution, I get minus over plus, which gives me the minus. So the minus corresponds to the positive y solution, and the plus corresponds to the negative y solution, which makes a lot of sense geometrically. If you're going, like dx dt being positive means you're going to the right on the curve. And if that's the case and you're on this ellipse, either you're going down if you're up here, or you're going up if you're down there. So that's why we got plus or minus. Does this make sense? Yes, no, maybe so? Okay. Another standard and somewhat famous problem that has appeared on many of my tests is the sliding ladder problem. So let us look at that. So the problem goes like this. You've got a wall, and if I'm feeling nice, I'll just make the wall vertical. Sometimes I make the wall be at an angle. That makes the problem harder. But let's make the wall vertical for today. And then you've got a ladder of a given length, and it's sliding down the wall. And then either you're given how fast the top of the ladder is sliding down the wall, the vertical wall, or you're given how fast the base of the ladder is sliding away from the wall. And you're asked to find the other one. So let's suppose we're given how fast the base is sliding today. Work that one out. So let me draw a picture here, what's going on. So example 3. Yes. So here's a picture of the situation. We've got a wall, all right? You've got a ladder like this, all right? There's the ladder, and it's sliding. And let's suppose I give you that the base of the ladder is sliding at 3 feet per second that way. All right? When this distance is, I don't know, 2 feet. All right? And we're also given that the ladder is a 10-foot ladder. Actually, instead of making that, I made it 2 feet. It is what it is. Okay? The question then is here's the question. How fast does the top of the ladder fall vertically at the given moment? All right? So as long as it's a vertical wall, what I do is I just give some names to things. I'm going to call the distance that the wall is from the base, the distance that the ladder is from the base of the wall. I'm going to call that x, and I'll call the height of the ladder from the bottom of the wall y, right? And I told you that this is a vertical wall. That makes things relatively easy in terms of finding a relation. How are x and y related? What's that? I just couldn't hear you.
It's a right triangle.
It's a right triangle? Yeah. Okay. How about this? X squared plus y squared, what's it going to be equal to? What I hear, you say what? 10 squared, so that's equal to 100. All right, I'm going to finally make good on my promise of not putting units in the calculation. I've been kind of half putting it in up to this point today, my bad. Okay, so great. Now we do what? We differentiate implicitly with respect to time. Differentiating this gives me that 2x dx dt plus 2y dy dt is equal to 0, which then tells me that, in fact, dy dt is equal to, minus 2x dx dt divided by 2y, which of course we could rewrite as minus x times dx dt divided by y. So what is dx dt and what is dy dt? I mean, we don't know what dy dt is yet, but can you guys tell me what's the situation here? Well, we have that x is 2, right? So we have 2 squared plus y squared equals to 100. Well, you're dead. Aw, man, too much. Fine. So that gives me y squared is equal to 96, right? Which gives me y is equal to plus or minus the square root of 96. So last time, the plus or the minus were actually both physically relevant, weren't they? How about this time? I think y equals 9.798 is the physically relevant solution here, right? Because it's distance, right? It can't be negative. We're not talking about a coordinate here. We're talking about a distance. So they're, by assumption, positive. And what's dx dt? Dx dt is given to be 3. Is it positive or negative? Is x increasing or decreasing? X is increasing. So that is a positive 3 feet per second. So here we go. We have minus 2 feet times 3 feet per second. I'm putting the units in the final step just so you see how they cancel. Divided by 9.798 feet. As you can see, 2 of the feet, they be canceling, and we're left with a negative value here, namely 6 divided by 9.798-ish. All right, so I got minus 0.612 as a good approximation to the answer here. There you go. Any questions before I show you guys another example here? Do you think you can do these? What do you think? Yeah? Maybe? I hope. Another popular example is something like this. You've got, car A, and you've got car B, and, A goes, let's say 30 miles per hour north, and B goes, say 50 miles per hour due east. Then the question is, if A and B start at same time, when A has traveled 60 miles, how fast is distance between them increasing? Let me make my picture bigger. So here was their starting point. So like t equals to 0, they began there, and then after a while, A has gone 60 up here, and B is over here somewhere. Whatever. It's not not to scale or anything like that in my picture, but this is going 30 mph. This guy's going 50 miles per hour. This is almost the same question as example 3. It's actually kind of almost the same question once you understand it. So we're asking how fast is the distance between them, right? So make a picture. Let's call the distance s right here. So this is s, let's say. I'm defining it to be that, okay? So with that introduction, my goal is to do what? So I'm trying to find what? Yeah, I'm trying to find ds dt, right? So what then? A squared plus, oh yeah, I think we need to introduce some other variables, right? Like maybe we should say x is the distance of A from the origin, and y, let's let y be the distance of, oh excuse me, x be the, listen, I'm exactly backwards, yeah, my bad. What I was trying to say is to, I was suggesting we call this distance the distance that A has traveled y, and let's call the distance that B has traveled x, right? What equation do we have then? We have x squared plus y squared equals to? Equals to s squared, right? That would actually still be true even if they started at like a different time. You know, even if they didn't start at the same time, that would still be true for this problem, if you think about it. Sometimes for these problems, we let the cars or the trains start at different times. And then you have to think about how to get their net distance from the origin through sort of, you know, common sense calculation stuff. But, so that's that. What else are we given? We're given that dx dt is equal to what? Dx dt is equal to 50. And we're also given that dy dt equals to 30. They're both positive, right? Because they're going away from the origin, their distance is increasing. I'm working in units of miles and hours, right? Miles per hour. What else are we given?
T equals 0.
Yeah, t equals, yeah, I defined the time they left at time 0, but that, yeah.
Are we given y equals 60?
We're given what? Y, oh yeah, y equals 60, very good. Yeah, we're given y equals 60 at the moment of interest. Y is equal to 60, so what does that make the time? Time equals to what? If we got 60 miles and we're going 30 miles an hour, how much time has passed from the initial point of their departure? 2 hours, right? Have you guys seen that horrible video of the guy with his girlfriend in the car asking her like how far they've traveled in the last hour, given that they were going 60 miles per hour the whole hour? It's a painful video. We should all experience it. Yeah. So 2 hours gives us 60 miles. But the thing is the same for both, right? So if car A has gone 60 miles, car B has gone how far? Right, so x is equal to 100 at the time of 2 hours. All right. Now, caution. Do not use x equals to 100, y equals to 60, or dx dt equals to 50, or dy dt equals to 30 before taking ddt. when I was first doing these things, I was in your place and I was doing these problems. On occasion, I'd be working one of these problems, minding my own business, paying attention, writing things down, doing things that were true. And then all of a sudden, I would have 0 equals 0. And I'd be like, what happened? Why? Why is 0 equal? I mean, it's true, but useless, right? So what happens if you take the data you're given and you plug it into the relation to start with, you can't study the change in the relation when you fix the values. You have to differentiate the unconstrained equation first, then plug in the data. I've done that in all the examples up to this point. You didn't really notice it. If I had plugged in the things that I was given first and then differentiated, I would have just got 0 equals 0 because there'd be nothing to change. So like, it's important that we differentiate this and we get 2x dx dt plus 2y dy dt is equal to 2s times ds dt. Oh, by the way, another important temptation to resist is square roots, right? What's the actual equation for s? S is equal to the square root of x squared plus y squared. You probably didn't even notice this, but instead of writing s equals to the square root of x squared plus y squared, which would kind of be maybe what you might write down just because you're interested in s, right? It's so much nicer to have the formula for s squared because you're not differentiating the square root. Square roots are a pain. Avoid them if you can. Anyway, so that's how the rates are related. Now I can take that and I can put the data into that, and that's fine. Now there's one other thing we need to figure out though, right? So s is equal to what? At t equals to 2 hours, what do we have s equals to? The square root. After all that talk. I just bad mouthing the square root, but eventually we're going to have to do it. Square root of 100 squared plus 60 squared. What's our distance actual? Actual distance is 20 times the square root of 34, which we don't care about. So approximately 116.62 is how many miles apart these two cars are after 2 hours, as the crow flies, right? And so I can solve for ds dt. ds dt is going to be equal to, divide by the 2, right? So I get ds dt is equal to x times dx dt plus y times dy dt divided by s, which for this specific problem with the givens that were given is 100 times dx dt was 50, and then plus y was 60, dy dt was 30, and I divide that whole thing by 116.62, and of course that's going to give me miles per hour since I worked in that system of units. And what's that work out to? I get a, whoa, I got 1842.9. I'm guessing what I did just now is I just divided this by that and then I added 1800. So let's try that again. So if 6800 divided by 116.62, and we get 58.31 miles per hour. Now another problem that is interesting that we could work if we had more time is you could look at like a trough of water, right? And you could imagine adding water to that trough at a certain rate, you know, liters per cubic minute, like cubic liters per minute. And if you're given like the shape of the trough in terms of like it's a triangular trough or something, you could study the rate of change of the height of the water as you add volume. So there are other problems past the ones we've looked at so far today to do, but I think that's a pretty good batch to start with. Tomorrow, we're going to circle back to logarithmic differentiation and do a practice session at the start on that, and then we'll go from there. So thanks, guys.